All right. Any questions?
So the only assignment that we have to like turn in after the lab is the master set 13 and 12?
Oh, the stuff that's still due?
Yeah.
Yeah, you got the master set 12 and 13 and the lab and test corrections for some people.
Okay.
And then the final test, but that's nothing you can do about that quite yet.
So do we have a date for the final test already?
I'm still picturing opening up March 7th. Not March. I don't know where that came from. Flashing back to those glorious days before a pandemic. December 7th, because of course it's the date that will live in infamy. And then you have through Wednesday to do it. But once you begin it, you have 3 hours to complete it. So you have 3 days in which to start it, but again, once you start it, you have 3 hours to finish it. Other questions?
Are you gonna like post the videos that you make on Blackboard, or are you just gonna leave it on YouTube?
No, they should be
Like,
posted. For the,
like for class on Thursday, are you gonna post like one video?
no, tomorrow is gonna be spent trying to get that organized so that you can find it easily. It should be under, lectures, and then just scroll down, they should be, ideally they'll be organized.
I wasn't sure if it was gonna be like separate from the ones that are already on there.
It'll be added on to, it'll be in that general area.
Okay.
No problem. Other questions? All right. So, we last left off. When we were using the long coil in the hallway, and we were showing bits of interference, that if I took a wave, sending it off to the right, and there was another wave coming from the left, when they would meet, you can just sort of imagine that I've got one wave here, I've got the other wave here, and you would just add them together. So if I have one wave traveling to the right and one traveling to the left, that when they meet, it would just be the sum of the two. And then it would sort of peak right there. And that's sort of what it would look like when they meet, or if there was a pulse being sent from below and a pulse being sent from above, that when they meet, if you add them together, you would get an idea of what the total would look like. So at this point, the bottom one is dominant. Over here, the top one is dominant. But in the middle, well, we get destructive interference because one is on the top side, one's on the bottom side, and you would end up with, let's see, oops, drew that one wrong. You go up like that. There we go. And so we have constructive interference because they produce something bigger than either the originals, or destructive interference. And at some point in the destructive one, if they are indeed the same size, just one's on top, one's on bottom, then when they're perfectly overlapped, then they should completely cancel out. And you saw this on Thursday in the vibrating string lab. So if I take something that is oscillating, for example, sound, with some set frequency and wavelength, and then on top of that, I put another sound. Well, if they're overlapping, then, well, you got some places where they are going to have constructive, some places where they'll be destructive. For example, right here, in this region, surely I can find a darker marker. That is constructive interference because they're both troughing at the same time. Whereas, let's see, was it a good place? Sort of right there, we get destructive interference because one is troughing, one is bottoming out in its pressure, and one is on the plus side on its pressure. And so we'll have destructive interference there. And let me grab the prop from the other room. So what I did to illustrate this is I created a sine graph of some particular frequency here. And on top of that, I created a sine graph. Now, the big difference, hopefully you potentially can see, is that one's purple and one's blue. But they are slightly different. That if you look over here, they both start on 0, they both go up to 1, but this one ends just after bottoming out, and this one is on the way down as it stops. But at a quick glance, can you tell the difference between the two? Besides the beginning and end, but do you know which one has a bigger frequency or a longer wavelength?
No.
All right, so, but they are slightly off. So what I did is I took the blue one and I traced it onto a transparency. Get those lined up. And hopefully you can see that it's obviously not a perfect trace, but the line I've drawn on the transparency should match relatively close to the blue line underneath. So now we can do a comparison of the two waves. And line it up properly. Static electricity. All right. So I have them starting out in the same place. They peak roughly at the same place, but if you can notice over time, the peaks start to get farther and farther apart. Lawson, you seem to be straining more than others. Let me bring it a little bit closer. It'll go on the tour. So you can see that they start out together, but then they get farther and farther apart as you go. I don't know why I'm assuming that you can see everything, Jesse. All right. And then I added them together. If you add them together, you get this pattern right here, where the amplitude is 2, because you're adding them completely. We get constructive interference. It's still constructive at this point because we have an amplitude bigger than 1, which was the amplitude of those two. But you notice that it is tapering off. If I extend it, because what I just showed you goes out to about there, so this is basically what I just showed you, but if you take it out even farther than was displayed on those papers, you get this pattern right here, where it's constructive interference to start with, and then we start getting into the destructive, we get to the point where it completely cancels out. This is known as a beat. B-E-A-T. And what it sounds like is the following. It's 440 hertz right there. So your eardrum is basically being vibrated back and forth 440 times a second. Here's 439.5 hertz. To me, it sounds a lot like what I just played, but it is different. Now, I'm going to play the first one again, and then I'll play this one separately. I'm just curious, because occasionally I have students who do have fine enough hearing. I definitely do not, but can you pick out the difference? Here's the 440 again. And here's 439.5. And out of curiosity, can any of you tell the difference between those two? Okay. Now, on the surface, it doesn't necessarily sound like there is any difference. However, if we play them at the same time, we can determine if there's a difference or not. We'll start out with the 440, and then I'll just add in the second one. And so we start to hear that pattern, the wah-wah pattern of constructive, completely destructive, back to constructive again. And now we get into the sophisticated math. So frequency number 1 was 440 hertz. Frequency number 2, 439.5 hertz. And together they produce the beat frequency. There's a certain frequency of the pattern there. And here's the sophisticated math. To get the beat frequency, so F's a beat, subtract. So 0.5 hertz. So was that a frequency of a half a hertz? Well, we can convert that into a time. If the frequency is 0.5 hertz, what would be the beat period? What is the relationship between frequency and period?
It would be 2.
It's the reciprocal, so it's 1 over the beat frequency. So 2 seconds. So let's find out if it gets silent every 2 seconds. 1001, 1002, 1001, 1002, 1001, 1002. Obviously, doing timing by counting is not perfect, but at least there's gives some sense that we're close. I assume this is the way piano tuners, back when I assume they still exist, piano tuners work is they play the frequency that the string should be playing, and then play the string, and they basically are looking for beats, or listening for beats. Now, if they get farther apart, so I'll do the 440, and this time I will do 420. Oops. 420. Here's 440, 420. You get much more of a trill there, because the beat frequency should be 20 hertz. It's the difference between the two, which means the period should be 0.05 seconds. And so it should be getting quiet every 20th of a second, and so that's why you sort of get that trill. Now at some point, you won't hear it. Because if I do 440 and 220, it sounds like two different notes being played. Now, there is a textbook that where I've seen this claim made, and I have yet to test it. I'm not quite sure how to test it. If you play something around 20,000 hertz, which is above what most people can hear, and then you play something at 20,000, say 440 hertz, again, above human hearing, well, there is a beat frequency here of 440 hertz, and the claim that this textbook made was that you would hear this at 440 hertz. Any software that I have ever seen, and I actually had a student who did computerized music, had very sophisticated stuff, they generally don't go this high. For some reason, software programs that produce sounds tend not to make sounds that are beyond the human hearing. Go figure. I thought potentially if I got 2 dog whistles and blew them at the same time, figuring with quality control that they weren't exactly the same, you might be able to hear it then, but I'm still not convinced it's true. Anyway, if any of you have a way of actually testing, being able to produce sounds outside human hearing, I would like to know. All right, questions to hear? All right, let's connect this up with some of the stuff we did last week. The red tube. I don't think I brought this out. I don't think I had it last time. All right, so it's obviously a frequency being played there. That's actually the second harmonic, third, fourth, and there's a fifth one there, barely. Here's the first harmonic. Yeah, you can hear that one. We'll talk about why we can't hear the first harmonic. All right, so the first harmonic basically looks like this. Because both ends are open, they are free ends. And I believe this was drawn on the board. You've got the 2 free ends. And a free end would indicate an antinote. That distance there is L. How many waves is this? So half of a wavelength is that length. And so the wavelength should be 2 times L. I know that since I'm producing a regular sound there, that V is equal to the frequency, speed is equal to frequency times the wavelength. So we can figure out what the frequency would be. So all I first need to know is what's the length. Now, it is a flexible tube. I can stretch it out, or I can just keep it as is. As it swings, it should stretch out some. So when I measure the length of this, I am going to stretch it out just a little bit. 1, to straighten it out, and 2, just trying to simulate some of the stretching that happens from swinging. Meter sticks going from there. And stretch it out just a little bit. And we are at 79.8 centimeters. So L, 0.798 meters. So the first harmonic would be 2 times that. .596. So in order to figure out the frequency that the first harmonic would produce, well, I have a speed, well, the speed of sound is roughly 340. Well, we'll just go with 340, as accurate as we get here. 340 meters per second is equal to the frequency, we're going to call it f sub 1 because it's the first harmonic, times the wavelength that is produced. And so 340 divided by 1.596. Let's do something.
113.
15?
13. Yeah.
13.
Yeah.
213.03
.03.
units?
Hertz.
Okay. Now this is what that would sound like. 213.03. That would be what the first harmonic sounds like. The trouble is, in order to get sound, we need to suck air up through this and get it to vibrate. The way that air gets sucked up through it is as I spin the tube here, the tip of the tube here is traveling faster than the bottom. Because this is traveling faster, the pressure up here is less than the pressure down here. And so air gets sucked up through it. The ridges are to get the vibrations going. You can also do this with a smooth tube, but you just don't get the nice sound. It sounds more like a, or at higher frequencies. But I just can't swing this fast enough to get air flowing through it fast enough. And so the first harmonic's not heard just because I would have to swing it, a speed something like that, and that's just not enough difference in air pressure to get anything going. But the second harmonic we can predict. Every time we do this, I add a wavelength. So L is to be equal to the wavelength because I add a half there and I add a half every time. So I get 340 is equal to 0.798 times the frequency for the second harmonic, or the first overtone. So that should be 416.06.
426.0.
Oh, 26. Sorry, can't do math today.
0.065.
So 426.065. Such a lovely sound. Now, in my imagination, because I want it to work, it does kind of sound like it. However, we can actually do a test a little bit better by doing them at the same time to see, do we hear the beats? Now, if this is dead on, and it won't be, if this is dead on, it just should sound like the same sound. You should not be able to distinguish them, other than they are different different timbres. Okay, thank you. This is plastic, obviously, and that's from the speaker. Now, let me put in my excuses now. One, the big one, it's a physics demonstration, so what are the odds? The other one, we found this in our backyard. It was buried in the ivy in our first house, near the barbells, and what I still assume is a dead body in there somewhere. It wasn't the best of neighborhoods. So let's play them at the same time. Let me turn this down some so you can actually hear. Here we go. there's a little bit of an extra trill there that wasn't there before, at least the way I hear it. A little bit of a one there. Now, I do that because I actually do hear that little extra trill. Do you?
Yeah.
Okay, at least two of you do. Three, all right. One does not. Two. All right, I'm gonna try this one more time.
Do you want more decimals
On,
on the thing?
no, more decimals isn't gonna do it. How much, let's see, 343, that's not gonna change it that much. I mean, we're in the ballpark. And there's obviously some oscillation there, but I'm definitely hearing it more that time than I did before. Some of you still are refusing to, okay. Fine, it was there. Perhaps you didn't hear it because it was dead on. Now, it is gonna get worse as we go. This is probably the best of the estimates. As we get the higher and higher harmonics, it seems to drift apart more. But let's go ahead and do the next one. Let's see. Started in the wrong place. Start up high, down, up, down. So now I have 1.5 wavelengths. Where the wavelength is equal to L divided by 1.5, which is 2/3 of 1.596. Oh, wait, not 1 point, that's wrong, 0.798. There we go.
849 or 0.89.
0.84, no.
What?
Oh, whoa, hey.
0.532.
Maybe a little.
One more time?
0.532.
532.
There we go.
And so the frequency of the third harmonic in this case, 340 over 0.532. Somewhere around there. Or it's just the sum of the other two. Notice, before we actually test that out, this one is twice that frequency. That's officially why it's the second harmonic. This one is 3 times that. That's why this is officially the third harmonic. All right, so 639.1. Oh, I turned it down. extra trill that I'm hearing, but not a great one. It just gets worse from there. But we are close. Yeah. There that is. Questions to hear?
So when the frequency increases, the pitch also increases, is that correct?
Right, officially, frequency is a property of the sound and pitch is a property of what we hear. I will use them interchangeably, just because I'm an ignorant savage, but habits are hard to break. Or maybe one's a physics and one's a bio thing, and I refuse to go by the bio thing. All right, so also, and this is just sort of a curious test. As you get older, you start losing some of the higher frequencies, being able to hear their higher frequencies, I assume. Roberto, you can appreciate it. So growing up, my dad had the TV on downstairs, and I would know the TV was on, and he couldn't figure out how I would know the TV was on because he had the volume down way low, and that's because I could hear the high-pitched sound that the TV was making back in the 80s and 70s. But he had already lost that register. I personally have lost it also, but I also have tinnitus, and so there's a range in there, so from about 10,000 to 13,000 hertz, which I can't hear. I can't differentiate it from the sound in my ear or in my head. But then it comes back briefly before I lose it completely. So I'm curious, I'm going to play a sound test here, and when you can no longer hear the sound, just sort of raise your hand. Oh, also, years ago I was on the site and I was testing it, and I had it at some pitch like 10,000 or at some frequency I could not hear. And